dying for each of the people in our data set, an estimated risk based on this model. Now we want to know is how good are those estimated risks? Looking at the -2 log L or the FAFT's information criteria is one way to measure how good those risks are. The C statistic is another way. What we can do is line people up according to their predicted risks. We have in this data set almost 700 people. Let's calculate each person's predicted risk based on this model, and let's line them up according to their predicted risk so that the person on the top of the line has the highest predicted risk, the person at the bottom of the line has the lowest predicted risk. A good fitting model would separate people who died from people who didn't die by this lining up. A good fitting model would mean that people in the top of the line with high risks of dying were going to be the ones who ended up dying. People in the bottom of the line with low predicted risk would be people who didn't die. So hopefully, lining people up by their predicted risk would discriminate those who ultimately died from those who ultimately didn't die. And that's what this C statistic measures. Really what it is, it says if you take two people at random, one who died and one who didn't die, and you say, what's the chance that of these two randomly selected people, one who died, one who didn't die, what's the chance that the dead person's risk would be higher than the non-dead person? What's the chance that he will be further up in the line than the person who didn't die? Well, that's what this 0.8 is. It's an 80% chance that when you take two people, one who died and one who didn't die, the dead person's predicted risk is going to be higher than the non-dead person's risk 80% of the time. That's a good number. We wished it would be 100%, so the closer this C statistic is to 1, the closer we're coming to discriminating the people who died from the people who didn't die by their lineup. So a good fitting model will give a high value for this C statistic. So it's another way to compare models. All things being equal, the model that has the bigger C statistic is doing a better job predicting high risks for people who died and low risk for people who didn't die. So it's another way of looking at the risk of a model in terms of fit of a model, to determine whether one model is fitting a data set better than another. Well, I think I'm going to stop here in terms of talking about models. And I'm going to shift gears for one last time and talk about one other topic because someone had a question about it. So if you're still with me, bear with me one last time. I'm going to try to minimize this. And I'm going to try to see if I can find, let's see, whether this will do it. Yes. So Aaron, if you're still with us, can you either send me a chat or come on to let me know if you've seen a different screen appear now? Actually, I'm going to, Aaron says, not seeing it yet, because actually, Aaron, I'm going to change it. I'm going to go back to my PowerPoint slides. So Aaron, now tell me if you see the PowerPoint slides. And the slide should say sample size and power. So you can, that's probably going to take a second. Not yet. So let's give it another 30 seconds. I'll take a sip of something to drink. And so in the last 20 minutes or so that we have, good to go, said Aaron. Great, thank you. So let me say a few words about sample size and power. And first I'm going to show you a few slides, and I'll show you one software package that can do many sample size and power calculations for you, but more often than not, they're not going to help you really do it the way you want to do it. Now, that's the message I'll end up with today. So let's see. Let me tell you a few simple comments about sample sizes and power. And what I want to do is link it back to a topic I talked about before, namely sampling distributions. So let's just remember what a sampling distribution is. Let's suppose you're doing a study like the one we've been dealing with, the Ohana mortality study. Let's suppose at the end of the day, we're going to calculate the mortality risk in the Ohana group. We're going to calculate the mortality risk in the non-Ohana group. And we're going to take the difference in those two. We're going to calculate a risk difference. And now what I want you to do is, in your minds, imagine you could do studies like this over and over again with the same numbers of people, but different people, similar in some extent to the people you have in your data set, same numbers of people in the two groups you're comparing. But now each of these other studies, you're going to calculate the risk of dying in the Ohana group, the risk of dying in the non-Ohana group. You're going to calculate a risk difference. And you're going to you're going to write on a piece of paper the value for the risk difference of all these many, many studies you do. Let's suppose you do 1,000 studies, 10,000 studies, huge number of studies. what you're going to have is a piece of paper with lots of values on it, each value being the risk difference from one of these studies. And now what you're going to do is try to describe that distribution. That distribution is called the sampling distribution, because your one study can be thought as a sample of many studies you could have done, just like the one that you did. And what you're trying to describe in a sampling distribution is theoretically what you would expect to see if you compared results from study to study. That's what a sampling distribution is. We're talking about the sampling distribution of a risk difference. Well, theoretically, you can describe that distribution. First of all, it's going to be approximately normally distributed. Now, a normal distribution is a bell-shaped curve. And the reason I say theoretically, these tables of risk differences, if you drew a histogram, the reason that histogram would look like a bell-shaped normal curve is because you're really looking at averages. If you classify your outcome as 1 if a person died and 0 if a person didn't die, and you calculate the average of all those 1s and 0s, the average of all those 1s and 0s will be the risk, the proportion of people who died. So when you do a risk difference, you're really comparing two averages, an average of 0, 1 outcome variables. And there's something called the central limit theorem that my thesis advisor always said that even if you don't understand it, even if you can't prove it, it's going to work for you. And the central limit theorem says that when you deal with averages, they tend to have normal distributions. And differences in averages tend to have normal distributions. And therefore, you would expect that the distribution of all those risk differences would approximately look like a bell-shaped curve. Also, theory tells us that the one risk difference we calculate from our study should be what we call an unbiased estimate of the true risk difference. The true risk difference is the risk in the intervention group minus the risk in the non-intervention group, control group. And the average of all those risk differences that you do, on average, will equal that true value, meaning that one of those studies might give you a risk difference that's a little bit too high, another one would give you a risk difference that's a little bit too low, but if you could average them all together, they'd give you the true value for the risk difference. And finally, the amount of variation from number to number on your list, in other words, the standard deviation of all those risk difference values on your piece of paper, will depend on the risk in the intervention group, R1, will depend on the risk in the non-intervention group, R0, but it also depends on the size of the study, the numbers of people in the two groups. And in this case, little n represents a study where you have the same numbers of people in each of the two groups you're comparing. So the point is that the variation of values to values in the sampling distribution depends on how big your studies are. Bigger studies are going to show less variation from value to value than smaller studies. And to see that, I ran some computer simulations. What I did, as I'll show you in a minute, is I essentially, with SAS, I said, let's consider a study where you have 50 people who have a risk of 10%, and another 50 people have a risk of 5%. The true risk difference you'd expect in that study would be a value of 5 percentage points, 10% minus 5%. Well, the theoretical slide on the previous slide said sampling distributions should be approximately normal, with the average of all the risk differences that you do from study to study to be similar or to equal that true risk difference of 0.05, and the standard deviation